And I will go ahead and get started by sharing screen. So today what we are talking about is we will be going through bonding. So this is bonding between atoms. And we've already kind of established a foundation for that by getting an understanding of electrons and structure of individual atoms, because if you know where electrons are and you know the valence electrons, then you're going to be in a good place to understand how those valence electrons are shared between atoms and a bond is formed between individual atoms. So to review that octet rule, this is kind of a golden rule of bonding and of how basically atoms want to operate. Atoms tend to gain, lose, or share electrons until they have eight valence electrons. And that could be eight valence electrons of their own, or eight valence electrons made up of six of their own and then two from another atom, or one from another atom. But they ultimately want to get to eight valence electrons. Now, just as a little bit of a reminder, for our main group elements, we have groups 1 and 2, that they have 1 and 2 valence electrons respectively. 3 through 8 have, well, as few as 3 valence electrons and as many as 8 valence electrons. Now, if you think about the octet rule and say something like an atom wants 8 valence electrons, then if you look at your noble gases, well, they have 8 valence electrons. So those noble gas elements, helium, neon, argon, krypton, and xenon, well, they have a complete octet. Now, one thing that I want to revisit here is that helium is an exception in that it doesn't want to have 8 valence electrons. It only wants to have 2 valence electrons. But basically every single other thing wants to have 8 valence electrons. There are some exceptions to the octet rule, but for right now, the exception to the octet rule that I want you to be familiar with is helium and hydrogen are two elements that want to kind of be an exception to the octet rule. Now, we have a bunch of common ions, and these ions are formed with an atom completing its octet or getting to an octet. If we look back and think about sodium, Na plus, well, sodium, what did it do, or what does it do to form that ion? It loses one electron. But then when it loses that one electron, it completes the octet. Now, this is what I was talking about, like the example where someone was like, listen, you're on the basketball team, you're on the varsity basketball team, you're not going to get any playing time though. So you can either be on varsity and never play, or you can drop down to JV and play all the time, which this isn't a perfect example, but if you've followed the NBA and any sort of free agency news, Chris Paul decided to join the Spurs because, well, right now the Spurs, they're going through some growing pains because they're a very young team, and he was told, listen, if you come join the Spurs, you're going to get to play all the time. Whereas if you go to not necessarily the Lakers, but a high performing team, you're going to be on the bench a lot. He said, well, I want to be on the floor. I want to play. Okay, so you lose an electron, you complete that octet. Chris Paul decided to sacrifice an electron. He completes the octet by playing with the Spurs. Now, there are a bunch of common ions, and all those common ions have specific names. Whenever something has a positive charge, that is known as a cation. Whenever something has a negative charge, that is an anion. So for a cation, like what we see basically for the top half of this right here, or the top 35–40% of this page, we see cations. So the sodium ion, potassium ion, the calcium ion. Anything with a positive charge gets blank ion. So if I lost an electron, you would know me as the Joel ion. Okay. Because, or if you see something that is something ion, you can go ahead and operate under the idea that that element, so the zinc ion, you'd look at that and say, okay, well, the terminology here is zinc, that's the element name, followed by the word ion, indicating that it has a positive charge. Anions, on the other hand, okay, so I'm going to write pos charge. So another way to look at that is more protons than electrons. Okay, now below that line, we've got negative charge. Whenever we're talking about in this, I'll use this term, a species, so an element or an atom that has a negative charge or an ion, negative charge is an anion. So anything with a negative charge is an anion. Now, the way that we adjust the terminology there is we take the name. So for instance, the element fluorine. If you're going to form the anion of fluorine, that is the fluoride ion. So we took the name fluorine and we replaced INE with IDE. So we introduced that IDE suffix and then added the word ion. So anytime you see that dash IDE ion, you should think, okay, this is an anion. So again, the jolide ion. I want you to see that IDE ion and think, okay, this is an anion. This is a negatively charged species. So that accounts for this middle section of this table. Now, the bottom section of this table shows where there are some nuances or complications. So if we look at this right here, we've got the element copper. Now, I'm going to bounce back for a second. Copper. Copper is Cu. Copper is right here. Copper is capable of forming two different ions. Now, these two different ions are both cations. They're both positively charged ions, but one is +1, and one of them is +2. Okay, so those have Latin names, cuprous ion and cupric ion. I don't need you to remember that, but what is more relevant and more commonly used these days is this, or the convention that you're going to follow is that Roman numeral there. So when you see copper 1 ion, that indicates that Roman numeral 1 indicates that it's a positively 1 or it's a positive 1 charged ion. Now, if you saw something like this, copper IV, well, that's the copper 4 ion. So those Roman numerals indicate the magnitude of the charge, and that charge is always going to be a positive charge. This is, however, reserved for metals that can form more than one ion. So we don't use that for something like lithium, because lithium could basically only form one possible ion. We don't say the lithium one ion because that would be, or that's unnecessary because there's not a lithium 2 ion, there's not a lithium 3 ion or anything of that sort. It's a lithium, or it's just the lithium ion. So you don't have to use that. It would be excessive to include that. All right. Does anyone have any questions about that? If there aren't any questions, I'm going to go ahead and bring up a poll. I'm going to close this poll whenever I'm finished eating this orange. And you can toggle back and forth between slides and everything like that. All right, the orange is done. So 4 out of 6 folks came up with the right answer, and that is the nickel 2 ion. That is correct. This is not the nickel ion because of the fact that the nickel ion can form, well, multiple different cations, which, yeah. Okay, so anywho, there we proceed. An ionic compound. So this gaining and losing electrons, we talked about this a little bit yesterday. We talked about chlorine, for example, likes to gain 1 electron and form what we now know as a chloride ion. Sodium, Na, likes to lose 1 electron and form the sodium ion. So when you have something like, when you go and you get some table salt, some NaCl, what you actually have is an ionic compound. This is a compound made up of a sodium ion and a chloride ion. Now, these two things kind of come together and make a really cool structure like this. Here's 1 sodium, here's 1 chloride, 1 sodium, 1 chloride, 1 sodium, 1 chloride, 1 sodium, 1 chloride, 1 sodium, 1 chloride. One of the things that's important to recognize about this is that this is like a perfect ratio, 1 sodium and 1 chloride. If you look at this and say, oh, but well, is this sodium right here associated with this chloride, or is it with this one, or is it with this one? To answer that question doesn't really matter because the ratio is 1 to 1. There's 1 sodium for every chloride, making up this kind of mega structure like this, and then making up a crystalline structure like what we can see with the naked eye. So 1 sodium and 1 chloride packed together to make this sort of structure. Now, ultimately, when you add this to water, well, then water is going to be able to disrupt and separate those 2 species from one another. Now, in order to put together a name, I think that this is a really good model because it makes it a little bit more intuitive. This table right here is going to be very helpful for putting together a name of a compound. So let's go ahead and toggle back and forth between this slide and the previous slide. So what we have here is MgNO and FeCl3. So Mg and O. Let's go back. That is that magnesium ion, and so Mg, magnesium, oxygen, O. Now, let's look at a couple of things here. Magnesium has a charge of +2. So that means that it gives up 2 electrons. Oxygen forms the oxide ion and accepts 2 electrons, giving it a -2 charge. Okay, so if oxygen accepts 2 electrons and magnesium gives up 2 electrons, those two actually work really well together because one is giving up two and two are giving up, and the other is accepting two. So if we wanted to put together a name for this, it would be magnesium ion plus the oxide ion. But let's face it, we don't need ion because we're forming an ionic compound. Those terms would be redundant. In addition to that, the magnesium ion is Mg2 plus, but we can see that this is one complete thing. So it's not going to be that, but rather this would be magnesium oxide. All right. Now the next one, FeCl3. All right, iron. I went back all the way here because iron is an ion that's capable of forming, or it's an element that's capable of forming multiple different ions. It can form the Fe2 plus ion or the Fe3 plus ion or even the Fe1 plus ion. Now, what those are going to be, well, Fe is iron, so we have the ferric ion or Fe, or sorry, iron 3 ion, and then chlorine or chloride. That's a Cl minus. So what we're going to do is we're going to combine those two. Iron 3 chloride. Stop. Sorry, that stop was for my dog, not for y'all. Continue learning. Um, so this is the iron 3 chloride, or it's iron 3 chloride. It's the iron 3 ion plus the chlorine ion, or the chloride ion. So then that's taking a formula and producing a name. Now we're going to go in the opposite direction. Name to formula. Now if we jump back, that was calcium chloride. So calcium is Ca2 plus, the chloride ion is Cl minus. So this would be Ca2 plus Cl minus. Okay. Now, if chlorine is going to accept 1 electron and calcium is giving up 2 electrons, well, then we've kind of got an imbalance there. I always like to think about it like this whenever I'm coming up with a ratio. We had a ratio of uh, sodium chloride. It's one Na plus and one Cl minus. Here, what we've got is Ca plus plus, Cl minus. We're forming a compound that has no overall charge. So what are we going to need for that compound in order for it to have no overall charge? Cl minus, another Cl minus. So I like to draw it out like this because that helps me kind of process and cancel these out. So what we're actually going to have is Ca, and then there's one Ca, then Cl. There's two of them, CaCl2. Okay, now to look at sodium oxide. Jumping back. Sodium is Na plus. Oxide is O2 minus. O minus minus, Na plus. There's one of them, Na plus. So we have Na2O. gets us our sodium oxide. All right. So now we're going to pull up another hole. Go back. And then this is NAF or NAF. Sorry that my poll screen and the Zoom poll are out of sync there. I apologize for that. Okay, I'm not going to use the timer of the orange. Instead, I'm going to take a drink of water. And we got 6 people who have done it. And 6 people, lo and behold, I think everyone should take a moment, pat themselves on the back. Not only because you got it right, because everybody got it right. So well done. Okay, so sodium fluoride is the correct answer, NaF. Fluoride has a charge of -1, sodium has a charge of +1. They work perfectly together. Here we're going in the opposite direction. Zinc oxide. Oh man, this is kind of tricky. So we're going to pull up another poll, but before we do, let's bounce back for a second. Okay, here we got zinc. Zinc 2 plus. This table right here should be a very valuable resource. Continue using this resource. I'm sorry, everyone, I have a puppy. And I have a non-puppy, but the puppy is the one that causes the problems. Okay, take a look at that. What is zinc oxide? Okay, we've got 3 people who have answered. I'm looking for 6. Okay, 4. I need 2 more, 5. One more person. Zinc oxide. Okay. All right, so we got 6 people. I don't know what's going on with the 7th person. Maybe I'm the 7th person. No, I'm not. I'm not. Okay, so here's our results. We've got ZNO, ZNO2, ZN2O. Let's talk about this one. If we go back to the previous slide, you can see that Zn has a charge of 2 plus, and O, oxide, has a charge of 2 minus. So effectively what we're looking at is Zn2 plus and O2 minus. How do we get those two things to have equal charges? How do we get these two things to come together to give us an overall charge? Let's talk about this right here. Zn2O2. If we had 2 plus 2's, that would be +4. Because anytime you have a subscript like this, number 2, that indicates that you have 2 of those. So you can multiply those charges. 2 times +2 gives us +4. Now over here, 2 times -2 gives us -4. Okay, so +4 and -4, those two come together to give us 0. Okay, that's good because that gives us a neutral compound. Now, with that said, though, whenever we look at a formula, we always want to reduce it down as much as possible. Your lowest common denominator. Can we reduce, like, this ratio is 2 zincs to 2 oxygens? We can reduce that down. We can reduce that down to 1 zinc to 1 oxygen. So that's why D is out, because that can be reduced. Now, if we look at these two answer options right here, 2 times +2 equals +4 plus -2 for oxygen gives us +2 for the overall charge of that compound. So this compound has a +2 charge based on those charges that we kind of accounted for. And we looked at the numbers of them. So that one's out. This zinc is +2. We're going to say +2 times -2 equals -4. Okay, so, or sorry, that would be -2. I apologize. So A and B, or ZN2O and ZNO2, are both out because they would not give you a neutral compound. Instead, they would give you a compound with a +2 or a -2 charge. Now, C and D are both correct, but C is more correct. ZNO is more correct because of the fact that you have a lowest common ratio of zinc and oxygens to one another. Now, these are compounds. These are different compounds made up of lead and different ions of lead. Lead-2, lead-3, lead-4, oxide. Okay, so let's take lead-2 and put together that formula. What's the charge of oxide? I need someone to add that to the chat. What is the charge of oxide? Oxide is the common ion of oxygen. If you jump back a couple of slides, you'll find it.
Isn't it -2?
It is. Perfect. So oxide is -2. So I'll write that down. Say this is -2. Okay. Now, lead-2. What's the charge of lead-2? Anytime you see that Roman numeral, add charge as a Roman numeral in the parentheses. So this is reserved for positive ions. So that would be lead +2. So what that means is that we're rolling in with a lead with a +2 charge and an oxygen with a -2 charge. And I wrote these as +2 and 2 minus. The placement of that negative doesn't really matter. The placement of that positive doesn't really matter. It's always reserved for being in the upper right-hand corner, though. So this compound would be PbO. Now, here's where it gets a little bit more complicated. Lead-3 oxide. Oxide is still -2. Lead-3 is, I don't know why it's doing that, +3. Okay, so here's a little bit of a trick for how to do this. Pb 3 plus and O 2 minus. The trick is you take these superscripts and you get rid of the charge. So I've got a 2 and a 3. And then you move those superscripts to the opposite ion as subscripts. So the 3, I'm writing PbO3, and then this 2 gets moved over here. So PB2O3. Now, that's not just some sort of elaborate, like, ooh, this is a fun, tricky way of doing this, but instead, let's think about this. We've got, let's take this formula right here and kind of digest it. What is this telling us that we have? We have lead and lead. Each one of these leads are lead-3. So they've got plus, 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 plus. Oxygen, I've got 3 of them. And each one of them is minus, minus. Okay. So this oxygen will knock out these 2 positive charges. This oxygen will knock out these 2 positive charges. And this oxygen will knock out these 2 positive charges, or kind of cancel out. So that's why we have these kind of, that's why we can use that rule, because we're trying to make this have a neutral charge. And that's how we do it with three oxygens that each have a -2 charge and two leads that each have a +3 charge. So then if we go over here, lead 4 oxide, that is Pb 4 plus O2 minus. Now, if somebody wants to add that to the chat or say it aloud, this is your opportunity to do that. I'm going to drink a little bit of water. You can do the exact same for this as we did for the previous one. So I'm going to scribble out my charges. I'm going to take my superscript for lead and make it a coefficient or a subscript for oxygen. My superscript for oxygen and make it a subscript for lead. So now I'm at Pb2O4. Now that I can simplify it a little bit. And I can simplify it in the same way that I simplified this right here. I can reduce these numbers, 2 and 4. These two numbers are both divisible by 2. When I divide each number by 2, I get PbO2. And that would be my formula for lead 4 oxide. The same thing goes for copper oxides. If you see CuO, okay, how do we do that? How would we possibly have that? What's the simplest way that we can have it? This is an oxide, so this has a -2 charge. Copper, well, if this overall compound has a charge of 0, what is copper going to have to cancel out that -2 of oxygen? +2. So this is copper 2 oxide. Okay, now for this one, I'm going to give you a couple of minutes to work on this and either add it to the chat or you can say it aloud. Translate that to the full name.
Is it copper 1 oxide?
Perfect, Javion. That is correct. Copper 1 oxide. Perfect. Great job. Okay. Now we're going to transition from talking about transfer of electrons. So one atom giving up electrons to, and then another atom accepting electrons, which is the hallmark of ionic compounds. Instead, we're going to revisit our octet rule, and we're now going to be talking about sharing electrons. So when we look at an ionic compound, this electron right here, sodium basically has no claim to it. It gave it up, chlorine accepted it, forming the sodium ion and the chloride ion. Now, what we're switching to is this right here, covalent bonding. This is where two different atoms share electrons between one another. These atoms share electrons, and typically, when we are forming a covalent bond, that is between a nonmetal and a nonmetal. So it is two atoms that are sharing electrons. Now, covalent compounds. So anytime you see a compound with a covalent bond, that is going to be known as a covalent compound. Just like whenever you see something that is an ionic or an ion, sorry, when an ionic bond is present, that is an ionic compound. Ionic compounds are solids at room temperatures, whereas covalent compounds are typically going to be gases, liquids, or they sometimes can be solids at room temperature. Whereas ionic compounds at room temperature are always going to be a solid. That's a very important distinction. Another important distinction is what they're composed of. So a metal and a nonmetal, or as a covalent, is a nonmetal and another nonmetal. Now, covalent compounds sometimes are going to be sharing of multiple electrons, leading to what are known as multiple bonds. So this right here, two hydrogen atoms. Hydrogen atoms like to have two electrons around them. And each hydrogen atom brings in a single electron. So this hydrogen atom right here says, well, I'm not happy. This hydrogen atom right here says, well, I'm not happy either. But if we each share our electron, we can form what's known as a single bond. So this line right here represents two electrons. These two electrons are shared between individual atoms. So, are shared between these two atoms. Now, a double bond. Well, let's think about this. This is oxygen coming in with 6 valence electrons. And what they're going to do is each oxygen atom is going to contribute to share a total of 4 electrons. Nitrogen, there are what's known as a triple bond, and this represents 6 electrons. So each one of these bonds is a sharing of 2 electrons. When you have a double bond, that's the sharing of 4 electrons because each bond represents 2 electrons. A triple bond is the sharing of, well, 3 bonds of 2 electrons each, so sharing of 6 total electrons. Now, with all of this in mind, where are these electrons? Well, these electrons are your valence electrons. What we're going to get into in the coming days is these valence electrons. What does this mean for all of the other atoms, other electrons? So, and we're going to go through the process of being able to put together a Lewis structure of a molecule. If we look at this right here, I know that kind of now looks like a face and now looks even more like a face. Ears, everything. I'm going to erase that. Went too silly. Uh, so this molecule right here, an O2 molecule, each oxygen atom is bringing in 6 valence electrons. So that means if this oxygen brings in 6 electrons, this oxygen brings in 6 electrons, that means we have a total of 12 electrons. So if we're to look at this molecule and say, okay, well, oxygen, oxygen, here's 2 electrons, here's 4 electrons. Well, we had a total of 12 electrons to draw. Now we're down to 8 electrons. Where are those other 8 electrons? And the answer to that is they're out here. These are electrons that are known as non-bonded pairs of electrons. So now what we can do is we can look at and basically split down the middle this right here. Say this is 1, 2, 1, 2, 3, 4, 5, 6. Then the other one, 1, 2, 3, 4, 5, 6. So that gives us our 6 electrons that each oxygen atom brought to the table. But remember that they're sharing. So I can go ahead and revisit this as number 6 and then say this is 7 for this oxygen. This is 8 for this oxygen. So this oxygen is happy. And then this oxygen is also happy for the same reason because it's sharing. So we can use this figure right here to put together a model without these lines. We can say here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We can have these dots representing our two individual bonds. Okay, well, we will continue on with that tomorrow. You guys have a quiz that will be posted today at 12 p.m. You have a quiz that was posted yesterday, and that will be closing at 2 p.m. today. You've got 2 attempts at that. There was an issue with a question on the exam. I adjusted that, and everyone should have, if you had that issue, if that was, if those points were deducted, they should have been added back. You should have seen your exam grade change. Nobody's exam grade was lowered by that. But anyway, I'm going to go ahead and stop the recording.